Okay, hi everyone. I think we can go ahead and get started. So on behalf of the AGSA, I would like to thank you for attending this workshop. Your presence is very important to keep us motivated on promoting more events like this. So it's a pleasure to introduce you, Dr. Raí Schwalbert. Raí obtained his bachelor degree in agronomy from the Federal University of Santa Maria, followed by a master's and a PhD in agricultural engineering from the same institution. Currently, Dr. Schwalbert is the Global Data Analyst Manager at Group Dongmario Group, also known as GDM. And today he'll be presenting us with his knowledge on spatial analysis. Please, Hai, feel free to take it from here.
Oh, excellent. Good afternoon, everyone. It's a big pleasure to be here with you guys this afternoon. I'm a former student as well from K-State. I spent a couple of years there with in St. team. So it's really nice having the opportunity to talk to you guys. And remember a little bit this amazing time. So the idea basically is to show you guys a little bit about this platform, Google Earth Engine, more related to how to use this on Python. I'm not long-term Python user. I start with R, so most of my background is R. More recently, I start with Python. Actually, when I start using this platform that we're going to talk about, Google Earth Engine, I start in JavaScript. That is also an option. And more recently, I moved to Python more because I want to use deep learning, TensorFlow, and that is a big advantage of moving to Python using this kind of approach with Python. But basically, I mean, exactly the same analytical power that you're gonna have using JavaScript, you're gonna have using Python or R. There is also an API for using R. That is also an option. I'm gonna share my screen. The idea is moving towards moving from a really basic starting point and then start going a little bit deep. It's not, I mean, it won't be a really advanced workshop on Earth Engine. It's more for knowing the platform, knowing the main functions, how to query information, how to apply some functions, export data, a brief idea about how to use algorithms there. But if someone is already I mean, long-term user of Earth Engine, probably is going to be a review. I apologize for that, but basically the main idea here is just have a really wide idea, broad idea how to access, how to get information, and how to process. Please feel free to interrupt me anytime. If you have a question about, just feel free to open the mic and ask me or interrupt me. There is any problem. The idea is to do this in a more interactive way. So please feel free. I'm gonna share my screen and let me see. Supposed to be this one. Just let me know if you guys are seeing my screen. It's okay?
Yeah,
Okay,
it's all right.
perfect. No, excellent. So basically this is a repo in GitHub where I just put, it's like 6 scripts where you have a really, I mean, the main functions that we're gonna cover here. If you go to the roadmap, we're gonna see basically the main topics that we're gonna cover. The first one is how to query information from Earth Engine, how we can get imagery, how we can get feature collection, that it's the vectorial files that we have, like a shape file, a GeoJSON, something like that. How to visualize that information. Mask is basically removing pixels or sections of the images that we don't like and we don't want to use in our analysis. How to map functions. It will be the equivalent for looping. Why we don't use for loop here on Earth Engine? Well, one of the main advantage of doing this on a platform like Earth Engine, it's the possibility of parallel processing. So basically, we're gonna use the Google infrastructure, and the main functions that we have, they are already prepared to parallel processing. So basically, all the operation is going to be performed in several machines, several clusters, and then Google will bring back and show the information and collect and show information for you. So that is the reason why even if you use Python on a notebook, or I mean, sometimes we're gonna not use standard functions like for loop, like apply, because that functions they will work on what we call client side. That is basically on your own machine, and we want to use the Google infrastructure, regardless if you are in a notebook or if we are in a web page using JavaScript. So basically, is the main difference. So basically we're gonna cover this, how to apply. For example, if you have an image collection, what is an image collection? So is a long list with several satellite imagery. So basically, let's suppose we get a Landsat collection and we want to calculate from one entire year, and we want to calculate any DVI for all the pixels across all this time series. So basically, we're gonna apply a map function and a function for a map and a function for calculating DVI. So that is the main idea. It's the equivalent of for loop to the for loop. Then we're gonna use the reduce functions. That is basically for those our users is the equivalent to the clear summarize. Is basically how to aggregate information across time or across space. Let's suppose we want to summarize the rainfall within a specific boundary. So basically, we're going to use one function from this family of functions that we call reduce functions. Then we're going to briefly cover how to import and export data. So if I want to bring information or export information from Earth Engine, how we can do that. Understanding the logic, the 5, the 6, and the 7, they are, I will not say advanced, but they are a little bit more advanced than the other points. That basically is in the understanding the logic behind image array. That is an operation that we're going to start using when we start building more complex algorithms. That is basically how to better storing the information from a collection of images in order to speed up the processing, and how to plot information, and finally how to a really simple example of how training machine learning algorithms. So we have, for example, the main classifier cluster algorithms are there. Random forest it's an option that we have there as well. Some options for regressions, the standard methods for regressions, like a linear regression, we can easily perform there. And also, I mean, we're not covered here, but also is available some options to use TensorFlow. So basically, you're gonna bring image from Earth Engine and apply convolutional neural network. For example, when using those images and those objects from Earth Engine as inputs. Also, it's a really powerful option that we have here. So basically here is our roadmap for the workshop. There's two options, as I mentioned. I mean, there's more, but I mean, easily we can say that there's two options for using Earth Engine without too many complication on settings. Basically, is use it directly on web, that you can, if you guys already have an account, you guys can go on, I think it's platform code editor, yeah, sorry. And then you're gonna have a screen here with a spot where you can type your code. We're gonna have a tree here with all the scripts that we already prepared. And then you can directly type your code here on using JavaScript and just play the results here. So this is a really simple way to use. And the second way is using Python on a notebook. I truly recommend you guys, mainly for those are starting, using this tool here that is called Collab. That is basically a notebook. There's no rocket science, but it's really easy to authenticate and use Earth Engine. So here we have an example. I'm going to start with this one, the script number 1. So if you guys have go to the GitHub repo, it's going to be this one. If I click here, open in Collab, it will open on a notebook. It's exactly the same than a Jupyter notebook for those are used to this kind of tool. So basically, we are using Earth Engine in a non-commercial way. So it's available for that. We can use for research. There is no problem, but every time I open a notebook, I need to authenticate. It's basically for avoiding for anyone developing a code and connecting on an API and deploying a service web that can easily becomes commercial. So it's just a step for avoiding this kind of behavior. So of course, when you use this on a company, on an industry, we're gonna have a paid account, and then we can skip this step of authentication. We're gonna do authentication using token, for example. That is something, will be something more automatic, and we can just avoid this first step. But here, as we use in the non-commercial one, we're gonna have to authenticate. So basically, I mean, for doing this is really simple. It's 2 chunks of code. The first one, we're gonna import this library here. There, I mean, for those are using Collab, there's no need to install because it's already installed. So basically, it's import and EE authenticate. And basically, this I'm gonna run. It's just a warning because this is coming from GitHub. Just a second. There we go. Allow. It's gonna pop up a window here. My account. Continue. And then the second one. Just remember to replacing this for your own project. So well, we are ready to use Earth Engine. The second library I'm importing here is a third-party library that is already installed in also in Collab, that is for plotting the maps. That is GEE map. Well, I just put here some examples of information that is available on Earth Engine because it's a platform for processing, but is also a repository where we have, I mean, hundreds or thousands of sources of data that you can rely on. For example, if you are interested on satellite data, I mean, there's plenty of options like modes. I'm just putting some options: modes, land surface temperature using modes as well. Sentinel-2, Landsat 7, 6, 7, 8, 9, all are available here. I mean, other satellites, Sentinel-1, it's also available. On weather, we have, I mean, I just put 4, but there is much more. GridMat, Prism, Open Land Map, Chirps for precipitation. So all this is available. Usually when I want to search some information, I use this page here, the same that we can use for processing on Java. And on this browser, we can just type what we need, for example, precipitation. And we're gonna see that we have some tables that are basically vectorial files, shapefile or geodesy, something like that, or raster files. And then here, if you go more, we're gonna see we're gonna have GridMat, for example. I'm gonna open this one, and then we have a description, the bands that are available, the minimum, the maximum variables that is expected for this band. So we have all this information, and here we already have the how to query that data. So basically, this is the code we need to put on. This is exactly the same on Java and JavaScript and Python for bringing this information. So I'm gonna close this just to wanted to show and go back to this one here. So here, just put some links for just for remember to comment. So I'm gonna start really basic, how to access and doing really simple processing on some imagery. So as you see before, this is the command, this is the function that is gonna bring query some data. Basically is EE for Earth Engine image collection. If you want an image for a collection of images, otherwise will be feature collections that you, if you want to query for a vectorial file. And this is exactly what you guys will find there. Look, if I replace that name for world climb view1 view, we're gonna bring this information here. I just bring in another source of information. That is the cropland layer from USDA. So I'm gonna print this. And if I want to see the image that are available, we're gonna use display function. That's gonna print 29 images. So if we go to features, is where we have the images. Look, we have images from 1997 to 2003. There is a delay of 1 year for USDA releasing those maps. So basically, this season will be released next year. So basically, this is just a way to print the size of the collection. It is not too important. Here also just for printing the names, but I mean we can use this or this. I prefer to use this one because it's a more interactive way to see all the images. But I mean, if you want to print in here, you can use this command. So I'm gonna just pass. Here, look, that is the way we can call an image collection. All the images with this code. If I want a specific image, I need to put this name here: USDA, NASS, CDL, in the year. That is what I'm doing here. I just replace image collection for image and then add the year here. And now we're bringing the CDL 2023. Here, we already have the first function, that is select. Select is basically for selecting the band we want. Because if you go back here, we're gonna see that most of these images are 3 or 2 bands. For example, this one has one band that is called cropland, another one that's confidence, and the last one that is called Q2. And here, basically, I'm selecting cropland. I could select 2 or 3. This is a list. There's no problem for adding more information here. So basically I'm selecting one. So select the bands. And there is also a function that we're gonna see in the next, probably next chunk or next script, that is filter. And filter is basically for filtering the image through a collection. So that is basically the difference between select and filter. Filter is towards image, select is toward bands. I'm selecting cropland, and then here I'm using the GE map. That is basically how we're gonna plot this information. If I run that, it's gonna return this beautiful map that we are seeing. Look, I didn't run this this chunk. That's why it's purple and blue, is because it's mixing information for all the 3 bands. If I selected this one and run, then we're gonna bring information from the cropland, and then it's gonna become in this way. So basically this is a 30-meter resolution layer where we have yellow, it's corn, green is soybean from 2023 season from entire US. So basically GE map start the function, then we're gonna add a base map that is this one, if we can interact with the map here. So if you go back here and remove the CDL, we're gonna see the base map. That is the hybrid I add. Here is just to set the center, one is start the map, and then add the CDL 2023. There is no need to be here. It's just to put a name, and this is if you want to specify some color, some different color for plotting a map. So if you remove this, it's gonna work as well. So basically, this is how we plot a map. And then, for example, let's suppose I want to draw a polygon somewhere here. I'm gonna go over Iowa or somewhere like on the Corn Belt, and let's draw a polygon. So how I just draw a polygon, how we can store that information. So if you go here and run this EE feature collection, and M is because we have this store on M. Draw last feature, that is this feature I just draw here, that is gonna create a feature collection. So remember, we have image collection for imagery, feature collection for features, for shapes and points or lines, something like that. And then here is the feature, it's a polygon, and then we can use a new function that is clip. That's basically clip this entire image for the boundaries of this polygon that we just create. And then I'm gonna plot again. And now I just clip it and I have a smaller image. It's really simple. It's really simple commands like select, clip. There's no secret. And then finally filtering. So remember, select is for bands, filtering is for image. Let's suppose here another example. Now I'm bringing information from another image collection. It's daymat for weather data. So basically, EE image collection for bringing the entire collection, and then I'm gonna filter date. So this is a kind of filter that we can apply, and here I'm gonna pass a range of dates from 1st January 2021 to 1st January 2022, 1 year. And then also I'm gonna filter bounds for my polygon. So it will bring only image that will make an intersection with this polygon. And so this is just for printing the size of this collection, and in here for printing the names of the image that we have. So basically running this, we're gonna have 365 images, one per day, because we're filtering for an entire day. So I think we can just play that if it's not too big, the image. It's gonna take it. Look, here we have on features all the collection, and then if you go to one image, we have the bands. So let's suppose I want to get, now we have this entire collection, and I want to get this image here. Okay, there's two ways we can do that. We can call EE image for this name here, or we can just select or filter for this the image that is on row, sorry, here on row 71. And then basically what we're gonna do is we're gonna call daymat, we're gonna turn to a list. I know that is more than 300 elements. We're gonna put 400 here. Just need to be a number higher than the size of the collection, and then we're gonna get the 71. And then just remember to telling Colab that this is a EE image, because we just turn to a list and then we need to turn back to an image. So this is another way for getting this specific image. We can do this or just using this code here is the same. What we have here also, it's just a simple exercise that we can do. That, I mean, let's suppose within this polygon we just draw how we can get cumulative rain from August that is higher than 100 millimeters just over the soybean areas. So basically here we start applying some data wrangling in order to mask this image, to filter pixels that we, I mean, don't want, and accumulate information. So basically this is we can do with a few lines of code, because look here, I'm just filtering, I'm using another kind of filter that is the calendar range. This is the standard way to apply a filter. It's called filter, and then within filter call an object that is EE filter. Before we just using one that is filter date or filter bounds. So this is just shortcuts for this. That is the standard way to applying. So if you want to apply more specific filters, perhaps we guys need to use this kind of structure here, because if you go back here and go to docs and type filter, we're gonna find several filters that we can apply. Greater, equal than, greater than, less than or equal, not null, within distance. So those are filters that you need to apply on the standard way. There is no shortcut for those ones. It's the same for this one I'm using, that is calendar range. So basically I'm filtering for all the images that are in August, because is that what I want. Then sum, apply this function that is sum. This function is apply over a collection, because this is a collection. So this is also a shortcut that you're gonna see later on the reduces, because there is, I mean, a standard way to apply a sum that is different from this. So this is the simple way to apply. This function is gonna sum up all the pixels that are stacking over a collection, and then we're gonna clip to a polygon, because we just are interested on this area of this polygon. So then we're gonna create a mask, because we just want pixels that are greater or equal to 100 millimeters. So This is also a Boolean function that is going to return 0, 1 layer. That is 0, 1 is lower than 100, and 1, that is 1 is higher than 100. This is also a Boolean operation that is gonna mask on CDL pixels that are equal 5, because I know that 5 is soybean, 1 is corn. If you go to the documentation of CDL, we're gonna see that for that layer cropland, there is numbers, and each number there's a map for a crop. So basically, I'm gonna build a mask here that is, again, 0, 1 is anything that is not soybean, 1 is soybeans. And then when we have this kind of layers that is 0, 1, black and white, we can remove those pixels that are 0. And how we do that? Using this function, update mask. So basically, we're gonna get this August day mat, that is this object that we already filtered to August. We sum all the pixels, we clip to the polygon, then we're gonna remove the pixels that are lower than 100, and then apply another mask, removing the pixels that are not soybeans. So that is what this chunk of code is doing. And then when I plot that, you guys will see here only the pixels that are soybeans and that have precipitation higher than 100 millimeters. So this is a really simple exercise that we can do with a few lines of code. So basically this is I'm gonna stop sharing. So this is the first notebook that we have that is basically how to query information, how to filter, how to select bands, and a little bit about the mask, how removing pixels that we don't use on our analysis. I don't know if anyone has any question here or any doubt. Otherwise, I can move to the second one. I'm gonna open here and then share my screen just a second.
Hi. Yeah, nice presentation. Can you hear me well?
Yep.
So when I try to authenticate in the fast code, I got some error. So it's not getting the authentication, but I followed your instruction, all the steps and creating the project. So is that something related with that? Like, should I do something with that account creation?
Did you replace the project, my project, with the one that you just created?
No, I just follow your script. Should I need
Okay.
to?
Yeah, I'm gonna share the second one and then I can show you. Just a second.
Okay, thank you.
No problem. Let me share again. Oh, how can I share screen? There we go. I'm gonna open the second one and this one. So here the idea is to starting applying functions across the collection. So if you get, as I mentioned before, if you get a collection with Landsat image and you want to calculate NDVI for all the pixels across all the time series, we can use these map functions. So I'm gonna open on Collab, and now I can show you where you need to change the project. So basically, this one here, if you already finished creating an account, it should go, okay, there's a step here. And then here is where you need to change and put your project. You need to create a Google project and replace here for the name of your project.
Okay, so I mean, in the first piece of code, I got the error before coming to the second one.
Oh, this one.
Yes, yes.
Okay. No, I can prepare later a short video how to create an account and how to authenticate, and then I can add I can add to the repository, to the repo in GitHub.
Yeah, thank you.
No problem. So I'm gonna quickly authenticate this one, and then we can quickly move to the next one, to the next script. Continue. There we go. So I forgot to mention something that is really cool from Colab. So if you click here and create a new chunk of code, we can use Gemini. So Gemini is a AI from Google that is equivalent to ChatGPT. And then we can just, ask for some code. For example, get precipitation data over Manhattan, Kansas from August 2023. It's not perfect, but it's really good. Help a lot. Look, it's importing E, it's creating a polygon, then is bringing chirps. That is one data set we can use. It's providing a sum because it's accumulating over August. And then here we're gonna have an error, look, because it not creating the map equal GE map. Then it's gonna create it's gonna plot and then just need to map. So let's see, it's gonna work. Yeah. It's not restricting to, for some reason, it forgot to clip over the region it created. If you apply clip here, it should work. There we go. Not sure if it's over Manhattan. Yeah. So as I said, it's not perfect, but sometimes helps a lot. I mean, we just have a really nice starting point for starting coding. Just to close here. And close this one. So here basically is the same. We're gonna define a region, and just, I mean, it's a polygon. Then I calculate in the centroid. I don't need to do that. I just put here as a piece of more of code. Then we are bringing Landsat data. So there is several classes of Landsat information that we can bring. We can bring top of atmosphere data, surface reflectance data, raw scenes. There's no treatment. There's no correction for atmospherical interferences or anything. Just pay attention the collection we are bringing for what you need to use this data. For example, if you want to use this information for training an algorithm for crop yield prediction, for example, for sure it's going to be better if you guys use surface reflectance. All these classes are available here. For example, if you go to Landsat H, we're going to see, look, there's tens of options. Tier 1 are images with lower quality, Tier 1 higher quality. Then we have top of atmosphere reflectance, raw scenes, and those there is no name, no specification. I think is surface reflectance. If you click here, you're gonna see, look, this data set contains atmospherically corrected surface reflectance. So there's the same for Sentinel, the same for modes. Here in the code, I'm bringing the Tier 1 surface reflectance. So basically, I'm bringing the image and I'm filtering for images that are over this region that is also Manhattan, Kansas. filtering date, I'm getting images from the beginning of 2022 to the beginning of this year. This part here is not important. I just put here because I want to, I'm gonna run and then I can explain this line of code. Look, this is an image. From, I'm just get a random image from this collection. Is the image number 9. If you just play the collection, we can see that which day is this. Just play and then put this here. I'm gonna run again. And then we have the collection here. I'm getting the number 9. So if I'm go to features, this one is the image. It's from 6th of January 2023, for example, as the image we're seeing below. There's a lot of clouds. I'm gonna show how to remove the clouds now, but this is basically a way to get a satellite imagery. Basically, this line of code, it's doing a really simple thing. If you go back here and open the same image that I just showed, look this one, and go to bands, you guys will see that this is important for those using satellite imagery, for example. You guys will see that we have scale and offset. So basically, this band 1, let's go back here. Band 1, ultra blue, band 2, blue, for example. Let's get the blue. Those values here, 1 and 65,000, they are not reflectance information because they are scale and offset. So in order to get the real reflectance values, you need to multiply by this factor and sum up this value here. It's basically what I'm doing here. I'm selecting the band I want, all the bands that start with SRB, and then I'm multiplying by that factor and sum minus 0.2. And then by doing this, these values here starting make sense because now I know that if I get the red, green, and blue bands and use those values, I'm gonna get a true color image. If I run the same code and removing this section here, you guys will see that we're gonna get the same image, but it's gonna be black or white or no sense. Because now those values doesn't look, it's a white image. We have values here, but we need to specify another quantity here in order to get a true color imagery. But we know if I know that if I get reflectance values from red, green, and blue, using those values will bring me a true color image. That's why I just multiply and add an offset. If I want to calculate NDVI, for example, there's no problem. We can do without this transformation because we're gonna use red and near infrared, for example, for calculating NDVI, and this transformation is applied for all the bands equally in this case of Landsat. So there's no need for, I mean, you can do if you want, but you don't need to do this transformation. So here, I'm gonna run again. You have the imagery. I didn't mention before, you can interact with this map. If you use this, there is an inspector tool here where you can use, and if you click here, it's gonna return for you the values that we have for each one of the bands. So if you have a band that is NDVI, it's gonna return the NDVI value for that specific pixel. Now I will show you how to remove the clouds and how to calculate NDVI, for example. And here, for doing this exercise of removing the clouds, there is a function, an algorithm that we can use for Landsat for removing the cloudy pixels. And then also a function that you can use for calculate NDVI. But look, we are working with a collection. So Landsat 8 that we bring before here, this is a collection. So this have 41 images. And for each image, we want to apply this function. For each image, we want to remove the clouds, and then later we want to calculate NDVI. And here is when we start using map. Map is the way for applying a function over all the images within a collection. So I don't want to enter on this. Later we can briefly mention what is this, but let's move to this one here. So here, the first thing we're gonna do is define a function. It's just Python code. I'm gonna define a function that is cloud removal and has X variable. And then what we're gonna do, X will be an image, any Landsat image. So basically what we're gonna do on X, I'm gonna select this band that is available on Landsat that is called QA pixel. And then we're gonna apply this operation here. That is, this QA pixel is different from a standard band. In a standard band, I have a number that is a integer or is a float, but it's just a number like 1, 2, 0.5. On this band, we have the information stored on a binary way. So it's just 0 and 1. And those functions, bitwise and, they apply some operations over binary information. So I'm not entering on this. So this is available if you go to here and ask for Landsat cloud removal. It's gonna bring you this function. But if you guys want to deep digger on this, it's basically a function that applies operations over binary information. So basically this is going to create, look, there is an equal here, there is an equal here. So every time we have an equal, a greater than, a lower than, it's going to create a Boolean. It's going to create a logical layer that is 0 and 1, 0 for what I want to remove, 1 for pixels I want to keep. So it's going to create this mask, and then I'm going to, on the same X, we're going to apply this mask. So basically is what this function is doing is storing on zeros, on pixels with zeros, pixels that have clouds. Because the identification of clouds, Landsat already did for us, and it stored on this layer that is QA pixel. So basically what we need is just retrieve that information. So this function here is gonna mask all the pixels. It's not perfect, you guys will see, but remove most of the pixels that have clouds. And then what we need to do is really simple. It's just map cloud removal. So applying this, it's gonna get this function and apply for all the images within this collection. Of course, if it's not well defined, it's gonna return an error, but if it's okay, it's gonna run. So on this collection, Landsat 8 mask, I already have images without clouds. It's the same than the last one, I have 41 elements, but without clouds. So if I remove this and just play Landsat 8 masked, you guys will see 41 is the same, but without the clouds. And then again, what I'm doing here, I'm just getting the same image. Look, it's the image on the row 9. I'm applying the same transformation, and I'm gonna plot over the previous one just to show the result. Look, this is the previous one. So if I close here, and there's a way that we can, oh, sorry, let's go a little bit here. If you click here, you're gonna see all the images that are available. So if you remove this one here, the true color, we're gonna get this one. That's already removed the clouds. Look, here we have a cloudy one, and here is the same, just we save the pixels without clouds. You guys will see it's not perfect because here it's going to skip some clouds. So this is an issue that we still have. If someone want to publish a paper, is a really nice topic, improving those algorithms for removing clouds. But I mean, it helped a lot, remove most of the area where we have clouds. Now I'm gonna just do one more example. It's the same. I'm gonna define a new function for calculating NDVI. Is basically get the bands 5 and 4 that is near infrared and red. It's gonna apply this function. This function basically get those bands and apply the formula for NDVI. You can type if you want. You can explicitly coding this, but I mean, if you want to save some characters, you can use this function here. And so basically is gonna get those images, apply the NDVI formula is gonna rename and add a band for the same image. We're gonna add bands. Which band? This one that you just calculate. Again, I get the masked collection that I just created and map and apply this function. So I'm gonna run this and this. And here we have the same region without the clouds in right now with NDVI. So if I click here, it's gonna bring some information about NDVI. So basically this is basically map is gonna do the same that we can do with for loop. Why we're not using for loop is because if you use for loop, it's gonna do, you guys will perform this calculation on your computer first, and second on a serial way. It's gonna perform the function for the first image, then when it's finished, it's gonna start for the second one. When it's finished, it's gonna start for the third one, and so on. And if you use map, you guys will see it's a 41 image, a really large image, and it's really fast, the result. It's because it's spreading across multiple computers, processing and bringing information back. Map, I mean, actually it's not sending one image for each computer. It's breaking down the image in several pieces, and each piece goes to one computer. So that's why it's really fast. And that's why we should avoid using for loop when you're working on Earth Engine. Finally, this one is the last one I want to show you guys on this script is iterate. Iterate is really similar than map, but it's like, I mean, let's suppose you guys want to perform a operation that the second step depends on the first. So we're gonna accumulate something or apply some function that where the previous result is the input for the next operation. Then you guys will use iterate, and that is a kind of function that you just, I mean, sometimes it kind of overlaps with map, but if you can use map, you should go with map because iterate is not possible for parallel processing. So it's gonna be a little bit slower compared to map. But sometimes for some operations, you guys, I mean, there's no way, there's no escape. The only way for moving forward is using iterate. Here, I just put one simple example. Let's suppose I have a Sentinel-2 collection. I'm filtering for the same region. I'm filtering for the same time interval. And what I want to do is for each year that I want to specify on this list. So this perhaps you guys could do with map still. I'm just doing on an iterate way, but perhaps this function, if you think a little bit about how you can code, you can end up doing with map. But still, look, here we have two inputs. We have one input that is an image, one input that is a list. So we're gonna apply a function using two inputs. And that is one example where we need to use iterate instead of map. So basically what this function is gonna do, here again, I prepare a function. This function is gonna get the first image of this collection Sentinel, then it's gonna filter this image for just getting all the image that is falling within this first year, that is 2019. And from all this subset of image from 2019, we're gonna calculate for each pixels the mode. Then it's gonna do again for 2020, then do again for 2021. So for each year, stacking the image across the time, getting the mode for all the pixels that are stacked. That is what this operation is doing. And then it's gonna store this on this empty list that I just created and return. So basically, how to apply that? Here we put the list, and here we put the image. So list, iterate, function, image. And basically this is perform this calculation. If you remove this and run again, run again. I don't know why I'm getting some error, probably because I forgot to run some previous code. There we go. I'm going to create a new one. Just play image. Looks taking more time because it's still processing. And then we're going to get probably here we have 4 or 5 elements because there's 5 years. So it's for an object with several images, we're going to return an element with 5 images, 1 per year with the mode of the value from each pixel and each band. The same if I want to, I'm not entering too much on this, but the same you can do if you want to iterate over 2 collections. Let's suppose we have a collection that is Sentinel from several years and another collection that is CDL. So when I start filtering, when I change the year on, for example, let's suppose I started an image on 2019, and then when I mask this, because let's suppose I want to retrieve only the soybean areas, I just want to get the soybean area on an image from CDL from 2019. And then when I move to a next year, I need to change the year on the other collection. So this is also an example that we need to do with iterate. So basically, it's what I'm doing here. I'm getting image the same collection, 2019 to 2023, and then I'm filtering the soybean areas. But every time I change it a year, I need to change the mask. I need to get the specific mask from the correct CDL. That's another example where you need to use the iterate. So here we define the function. We have one collection that is CDL that is here, in another collection that are the images that I just created in the previous chunk. And this will do the same. If I run that, probably there's something wrong here. Let's rerun this one. There's a count. There we go. Image 2. Then it's gonna display this the result of a new collection with masked image. So basically, the idea here is just to show you guys 2 really important operations that we use all the time on Earth Engine. That is map, it's similar to for loop when you guys want to apply a function over a collection, and the iterate is basically most of the times when we have a dependence on the previous input that is going to be a next the output is going to be the next input, or you're going to have 2 collections and then you need to apply the function but using 2 inputs instead of 1. Then also you guys need to use iterate instead of map. That is the main difference. But remember, iterate is not perform on parallel. So If you guys can use map, you should prefer use map. That is the main idea on this second script. The next ones are shorter, so probably we're gonna good on time. I'm gonna stop here and just why I move to another script if someone have a question on. Yep.
Yes. So again, Dr. Raí, you show something like in the cell using the artificial intelligence Gramini to create the code. I would like to know that one. And another question I have, can you use UAV derived orthomosaics in Google Earth Engine and do like removing soil or removing shadow or clouds?
Yeah. Gemini, I'm using a free account, so it's really limited what you can do with this AI. But I mean, it's available for using. I'm using most of the times I'm coding on Earth Engine. I finish using this because it helped me a lot to. Sometimes I don't remember how to change the color when I'm gonna plot an image, so I just ask, and then it's gonna bring some information that most of the times are really useful for helping me to speed up the coding processing. But it's free for use. I mean, you can. Anytime you open a new cell for putting the code, it's gonna have the option for asking help for Gemini. And the second question related to orthomosaic, yes, you can do, but it's going to rely on third-party libraries that is available. So if you search on GitHub, probably you're going to find some information on how to do that. And basically, the idea is instead of querying the image using EE image collection and the code, it's gonna you will upload the image to an asset that is available on Earth Engine. I'm going to share my screen and then I can show you. If you came here, look, you can have an option that is new, and you can upload an image, a shape, a CSV, for example, and then from here we can start applying the functions. So there is some libraries that already prepare functions for running on parallel, because that is the main advantage of Earth Engine, and is not supported by Google. At least in initial steps, when I searched that, I didn't find functions that are supported by Google, but there's options that were developed by the community. So I'm gonna
Thank you very much.
No,
Yes.
no problem.
And the 41 images that you are working with from Sentinel-2, did you already collect and pull it in some directory, or you are connecting it with the server?
No, it's all in the cloud. Now on this step, that is step 3, is when you finally will download information. So until now, all the information is on temporary memory on the cloud. So when you close the notebook, it will disappear. So basically, after we finish the processing, then we can download the information. And that the step that takes a little bit more time, because you're bringing the data to a local drive, for example. Or usually I'm gonna open here, and then you're gonna see that most of the times we're sending to Google Drive or to assets or our assets, but it's the step that is gonna take more time. So I'm not spend too much time here because it's really simple. Look, let's suppose we finish the process and we finish with an image or a collection of images, and then we want to export that. And basically what we need to do, I'm gonna quickly run this and then I can show. And then what we need to do is just to run one function, and then it's gonna send directly to the Google Drive, because as you guys are working with Google, it's all connected. So oops, it's really simple. Continue. Look, I'm gonna quickly run this. It's gonna load a feature collection that's a vectorial file. I'm just getting some, this is the boundary of Kansas, Colorado, and Oklahoma, basically. Then I'm just plotting here just to see. There's nothing new here. It's just a GE map function. I'm gonna summarize some information. Oh, here, sorry. I thought it was in export, actually it's reduce. Sorry, this is a little bit more important than exporting. I'm gonna pass over reduce, and then the next one is export. Sorry for the confusion. But basically, what I said is true. It's just bringing some states, plotting the data, and here we're gonna summarize the information. Sorry, on the script 4 is gonna be the export. This one is the summarizing, is the reduce. So basically, this we're gonna use when you guys want to summarize information over time or over space. Let's suppose here I just get weather data from Prism from one entire year. I'm selecting the column precipitation, and I'm calculating for each pixel an standard deviation. We could use another function that could be mean, could be sum, but in this example, I'm using standard deviation, for example. So basically, this is reducing over time, because for each day, this is a daily collection, so we have one image per day. So basically, for each pixel that is stacked over the entire year, we're going to calculate the standard deviation. And then it's going to do with this reduce and reduce standard deviation. In the first scripture, I mentioned that we could use, for example, if you want to sum, we could apply a shortcut that is sum. Well, this is equivalent to this. When we apply a reduce, we call a reducer. For standard deviation, there is no shortcut, so we need to use the long format. So basically, applying the reduce and clip the states. So I start with an image collection, and I finish with an image. That is this one here, because I compress all this collection to an image where each pixel has the standard deviation for the precipitation of the entire year. So if I click here, oh, let's run again, sorry. If I click on inspect, and click on a pixel, we're gonna get the standard deviation, 73.15, for example, for this specific pixel. So this is how to reduce over time. It's really simple. And then what you guys need to do is just to change the reducer to apply another function. And then if you want to search for new functions, you can go here and docs, reducer. And then you guys will see that have here all non-zero, bitwise, that for binary bands, circular mean, count, first, last. Well, there's a lot of options. Percent correlation, and then that's the way you can apply a function over time across the collection and summarize a collection, turn it in an image. In the same way, following the same rationality, you can summarize over time, you can summarize over a region, for example. And then here again, I'm getting Prism from the same period, the same band precipitation, and we're gonna apply this function here that is reduce regions. So here we have an image collection. In here, we apply a reduce regions. So basically here, we're gonna calculate the median within a region. Could be the mean. We can replace this by a mean. There is no problem. Then we're gonna calculate the mean precipitation from an entire year to over Kansas, Colorado, and Oklahoma, because that is the states that we define at the beginning of the code. Then it's a good practice. Just put here the scale you want, because sometimes Google Earth Engine cannot retrieve the correct scale. So basically here, this is the way we can calculate the projection and the scale of this image. We're gonna use the this function here, that's projection, is gonna return the projection of the image, and this, as we have the projection, if you apply nominal scale, is gonna return the resolution. So if I run this without this section here, it's gonna just print here for you guys. It's the resolution of an prism image. It's almost 5 kilometer, and that is the projection of the image. That is using a specific projection for United States. And then here, what I'm doing is just saying the scale is this one here. If I want a different one, there's no problem. I can put 30 here. And then it's gonna split the pixels in smaller pixels. And I mean, the result will be the same. The calculation is gonna take longer. So there's no reason for doing that. I can do in a different direction to me. I can say, I want to use 10 kilometer. Then what Google will do is, Google Earth Engine already have several tiles of the image, several versions of the tile. One is on the native resolution, for example. The native resolution of Landsat is 30 meter. Well, we have one tile with 30 meter, but Google also have stored on memory a tile that it have, I don't know, 60, 90, 100, and for starting on the native, going up. So basically, if you guys want to apply this function on a tile with a coarser resolution, you guys can do it. There's no problem. Actually, the issue you might have is the final value that we're gonna get for average for the statistics you apply. I mean, won't be exactly the same, because we're doing two operations. First, we are aggregating for a higher pixel, and then we're applying. But sometimes, so if you have a really heavy process for applying, you can change a little bit the scale in order to speed up, and we're gonna lose a little bit of precision, but sometimes it's needed when you guys are applying a really complex operation. On this case, I'm gonna use the native resolution that is one I start here on res. So basically this is gonna calculate, I'm gonna remove this one and plot stats. It's written an error because it's all connected in my notebook, sorry. Oh, it's because of this. There we go. So this case, I start with an image collection and I finish with a vector, with a shape. And this here, we have 3 polygons, and within each polygon, if you go to property, we're gonna find one that is mean. And that is basically the information I summarize. If I change this for another statistics, it's gonna return a different one here. So basically that is the way we reduce over regions. And then we start with a collection of images, and we are gonna finish with a shape file or a feature collection. And when we summarize over time, we start with image collection and we finish with an image, because it's gonna reduce all the images into a single image. That is the way we can summarize. And if I want, for example, let's suppose I want to reduce, but I want to reduce over a year. For example, I will get a really long time series from 10 years, and I want to sum the precipitation for each pixel on intervals of 1 year. For doing this, I want to use two functions. First, I'm going to prepare a function where we have a reduce, and then we're going to map or iterate perhaps, because we need to specify the years. And then when we start building a more complex function and start mixing reducers, filters, map, iterate, all these kind of things. But that is the main idea of reduce. That is the way we can summarize information across time or across the space. That is the main idea. I use a lot this kind of functions because most of the times we want to summarize information. It's really useful. Now finally we can go to the export. I'm gonna just change the notebook here.
Before going to the next section, right? Just a quick question. Say you plot the precipitation, but there is no legend. How do you know that which one is more precipitation or which one is the less precipitation? This is one question. And second question is, say, I'm kind of confused. How do you measure precipitation with pixel? Like, can you explain a little bit? Like, we know pixel can be the reflectance can tell you about the vegetation or healthiness or whatever. But with precipitation, just a little bit explanation.
No, yeah, sorry. I'm going really fast, so sorry for the for this confusion. The first one is basically it's a matter of putting a legend on the maps. So basically, I'm not paying too much attention on visualization, but basically, I mean, using this library GEE map, we can easily include a legend or something that is gonna reference, and then you can easily see that perhaps the blue is gonna be higher precipitation, the red is gonna be low precipitation. So that's one way you can do that. Or now we're gonna see that when you export the data, then we can open on on ArcGIS, on QGIS, for example, and then we can click and see the real value of each pixel. And also you can use the inspector of the GE map, and then if you click on the pixel, you're gonna see the real value that we have for precipitation. So, and then you can retrieve some more information related to each pixel and how we code with colors. And related to this idea of having a value of precipitation per pixel is basically because we have different classes of raster. For example, the first one that I show, or initially, the first thing we think is a picture. For example, a Landsat imagery, a Sentinel imagery, where each pixel is the reflectance of a specific band from a sensor on the satellite. For example, we have near infrared, and then we have a value for reflectance on a range of wavelength that is related to near infrared. The same for blue, the same for red. So this is one class of image that is satellite reflectance imagery. Then we have another kind of imagery that is still a raster file, that is a matrix. We have several pixels, and each pixel store a value. It's not coming directly from a sensor on board a satellite, for example. It's a process, a model that is creating this image. That is an image where we have each pixel on a resolution that we can define, that the model will define initially, for example, 5 km. And then we're going to store for a specific day the amount of rainfall that we have for that, on average, for that region. So it's not coming from a satellite or directly from a satellite, directly from a drone, for an airplane. It's coming from a model that is preparing this image. It's basically already that is something that is already processed, is available for using. That sometimes we have pixels with evapotranspiration, precipitation, solar radiation, this kind of information that is not coming from a sensor, basically.
Oh, but all those are stored here, right? Okay.
Yeah. Well, I mean, the way we store the data is the same, is a raster file. that is in the end of the day is going to be a matrix or a tensor, because sometimes we have more layers and more that are the bands or the time.
Yeah, thank you so much.
No problem. I'm gonna. Well, look, this one here, it's really simple because perhaps we don't even need to execute this script. I'm just gonna show here because there is no mystery. It's just authentication, how to initialize, and then here is the same we do in all other scripts. We're gonna bring a collection. We're gonna filter for a date, for a region over space, and I'm gonna perform some operation. Reducing, mean. I'm gonna renaming, clipping, and then I finally will export this information. And then here we're gonna use, this is just arguments that we're gonna pass to the function. For example, image is the name of the image we want to export after a whole process within Earth Engine, for example. And then monthly LST, land surface temperature, I just created here. Then the description is just a name. It doesn't matter. It's just for when you're tracking the download, you're gonna use this name just to know if it's already finished or not. Let's suppose you have like 6-7 processes making download at the same time, and then we want to know if this one is already finished, because that's why we use this description. Then again, scale is the same. It's a good practice to write the scale we want to export. Let's suppose you're exporting a Sentinel-2 image, then you guys want on the native resolution. Then we're gonna write 10 here. This is always meter. On this case, the native resolution of this image is 1 kilometer. That's why I put 1,000 here. Region, it's because let's suppose I want to export over a specific, just over the image that is intersecting a specific region. That's why I'm gonna use region. Otherwise, if I remove this one here, it's gonna download the entire image. And the folder is basically the folder within Google Drive, because it's already connected. How I know that is Google Drive, because I'm using this function here, batch export image to Drive. And then I know that it's gonna send to my Google Drive. Which folder? There's one here. I can replace to Drive and to input to asset, and then it's gonna send to here. That is kind of a bucket that I have within Google where I can store some information I can easily retrieve and use in my code. There's another options. You can send to a cloud storage in Google if you are already using like, this is more for, and then you need to pay for storing this information. Usually I use Google Drive or assets that are free. The same for, so this is for image, and then you're gonna define this is as a task, and then task start is gonna start downloading. And then if you want to track and to know if the download is already completed, you can use task status, and then it's gonna say ready, completed, running. Ready means that is ready for starting downloading. Then we have a status that is running, that is still downloading, and the last one is completed when it's already available on the drive. The logic is exactly the same if you want to download a feature collection, that is a shapefile or a CSV, for example. You're gonna you need to have on the temporary memory of Earth Engine the feature collection you want to download, and then you're gonna define the parameters. Look, collection is the name of the collection. Description, again, is just an ID. Folder is the folder where you're gonna store the information within Google Drive. And file format, here we have some options. Shapefile is one of them. Then it's gonna download as a shapefile. If you go back here and put export, Then we have export table, look, to drive, to view, to cloud star, to BigQuery, to asset. Let's get drive. And then we can see, you can download on CSV. Then you're gonna get a table, and the geometry is gonna be stored in a column of this table. It's in a format that is, I don't remember exactly the format is gonna start, but it's basically, it's gonna store the geometry as a text, a GeoJSON, KML, KMZ, shapefile, and this one, it's a geospatial format, but it's prepared to enter on a TensorFlow algorithm. So this is more on deep learning side. Then we can prepare information and get from Earth Engine and then feed into a deep learning model, for example. Also, the same for image. We have different options of formats we can export an image. If you go here, image to driver, you guys will see there's some options to export image. So this is basically how to download data. The 5 and the 6 are really, I mean, I'm gonna pass really fast, just to show you guys this is also available on Earth Engine. This is for more complex algorithms you guys will run. It's sometimes I use, it's really important. It's just to look, I'm too many sections open. Let's close, terminate all. And then you can start this one here. So this is similar what we do with reduce, but instead in reducing, we're going, let's suppose we have an image with several bands, or we have an image collection with several images. When we apply a reduce, we summarize all this value. For example, here we have 3 bands. This is one image, 3 bands, RGB, for example. When we apply a reduce, reduce mean, for example, we are gonna average those values, or reduce sum, we're gonna sum up those values. When you apply this function here to array, we also will summarize the information, but instead of performing any statistics on that, we're gonna store the values on array. So basically, we move from one image that has 3 bands and finish with an image that has 1 band, but within this band, we have a vector, or an array, on a matrix, but I mean, we're storing multi-dimensional information within a pixel. So change a little bit the standard notion that we have from a pixel. That is, I mean, instead of storing a value, start storing a vector, a matrix, or an array tensor that have multiple dimensions. When this is important, mainly when you guys go to deep learning. So this becomes really important, because then we can store and manage the information in a really clever way that is going to be really important when you guys want to use deep learning. Not only for deep learning. Here we have an example that we're going to perform a linear regression, and it's really useful for linear regression, for example, as well. But I just to show you guys that this is also available and is a really important tool within Earth Engine. So here, if I have a band, we're going to store if I have an image, we're going to store the band values within the pixel. If you have an image collection and apply the same to array function, then we're going to have again an image, but within each pixel, we're going to have a matrix. On the rows, we're going to have the dates, the different image that we have. The pixel coming from the value of the pixel coming from a different date. And on the columns of this matrix, we're going to have the bands. So I have like a matrix within the pixel when you apply to array to image collection in this case. So basically here we have a really simple example. What I want to do, I want to perform for each pixel, I'm gonna get a collection. For each pixel, I want to perform a regression. How can I do that? Because since I have a collection over time, my predictor will be time, will be the date of the image, and my y, my response variable, will be the reflectance. I'm gonna use NDVI in this case. So for each pixel, I'm gonna perform a regression over time, and then I'm gonna retrieve the slope. So doing this, I'm gonna create an image, and the value of this image will be the slope of this regression. Basically, I'm gonna see which pixel is changing more NDVI across time or less, because this is the value, or on a positive manner or in a negative manner. So this is basically the operation I'm gonna perform here. This, it's what we already see. I'm gonna get a starting date, a ending date, latitude, longitude, create a region, define a function. What this function is gonna do for each image of this collection, this function will store one band that is just the number 1. I just need to this for the way the Earth engine operates for performing linear regression. It's for calculating the intercept. It doesn't matter why, but it just need to have a band that is 1. Another band that is the year of the image. So we're gonna, all the images coming from 2000 will have a band that will have a value that is 2000. All the images coming from 2001 will have a band that have the value 2001, and so on. And an additional band that is NDVI. So this image will do all this and add bands at the end. Here, I'm just querying the collection, filtering the date, getting the specific dates I want. Look at here, I have a different filter that is day of year. Filtering bounds for restricting images over this region, specific region I want, and applying map lambda. I could just apply directly data prep if I want. This is more Pythonic way to write this, but I mean, it's also valid. I'm applying data prep over this collection. And when I run this, if I come here, I'm finished with an image, actually a collection of images. I'm just plotting one, but I have a collection. So image is a collection of images where we have a band. So if we click here, where guys will see we have a band that is a constant, that is the one I just added before. Then this is a normalized value related to the year. It's not exactly 2000, but it's normalized to values between 0 and 1, being 0 the initial year, 1 the last year. And ND is an NDVI, the value for NDVI for this specific pixel. As we have one here, I'm plotting one image. We have on the collection, I have several. What am I gonna do now? For each pixel, over time, apply a regression. How can I do that? Using the idea of arrays. Look, the first operation I'm gonna do, I'm gonna apply to array. Image is a collection, so I'm gonna finish applying this logic here. A collection to an image where each pixel is a matrix. So this is what this function will do. And then this is just to store 0, it's for rows, 1, it's for columns. It's the dimensions of the array. So basically image axis, the axis of the array where we have time, the image. Band axis is the columns of the array where we have the bands, the constant, the year, and then NDVI. So if I plot that, I'm gonna click here, and then now you guys will see that we don't have anymore a value for a specific pixel, a value, but we have array. Look, for this pixel, we have an array. So this is the first row of the array. Look, this is the first row, first column. First row, second column. First row, third column. And then we finish the first row. Now we have again, second row, first column, and then so on. So for one specific pixel, we have a huge matrix. And finally, here, where we're gonna apply the function, we are gonna use this array slice that is really similar to what we have in Python when we start cutting, slicing an array. So we're gonna create a new image array where we have just 2 columns that are the X is the 0 and 1. Here is exclusive. So if I put 0, 2, Python understand that I want the first and the second column only. So I'm navigating on the band axis and getting the first and the second column. That is the constant value and the year value. And for Y, I'm navigating on the band axis and getting only 2. That is the NDVI. And then when I apply this function, matrix solve, X over Y, it's basically perform a linear regression, being Y the response variable, X the predictor. So basically, if I run that, I'm gonna finish with an image. Here I'm just getting the slope. So this image here, it's the slope. So basically, pixels that are, let's get a value. Pixels that are positive and have high values in positive values, it means that an NDVI increase over time. If have negative values, it decrease over time. That is basically the logic of this. Look, minus 0.04 for this shadow area here. It means that over time, NDVI decreases. If I get a white one, probably gonna get a positive value. 0.003, it means that this pixel NDVI increase over time. So this kind of data wrangling, feature engineering is really useful when you're gonna start going for algorithms that will classify pixels, for example. Let's suppose I want to differentiate a corn from a soybean pixel over time. So I want to build a crop classification map. So before running a random forest, before running a classification, any algorithm I want to use, it's really useful perform some feature engineering as this one we are showing here, because then we're gonna summarize information and decrease the amount of input we're gonna put in our model and avoiding saturating it. So this is a kind of example where we can calculate the rate of change of NDVI over time for each pixel, for each region on space. So this is, it's a little bit more complicated. I know I passed super fast, but I just to show you guys that is also an alternative that you guys have and is really useful when performing operations on Earth Engine. And now I'm gonna move quickly to the last one. I think 5-10 more minutes I can finish. I just want to show one example of how performing a machine learning algorithm, for example, how to use a machine learning algorithm on Earth Engine. That is, the idea is how to split the data between training and validation and apply a really simple classification model. Let's get this one here, the 6. So this one, it's a really simple code. There's just few chunks of code. I'm gonna start authenticating. Allow.
You are not sharing this screen.
Oh, sorry. Thank you. There we go. I'm just authenticating. again, importing GMap, starting the project. Those are the initial steps are always the same. Now, what this huge chunk of code doing here is nothing special than simulating data. So if you guys have a shapefile and want to upload, it's going to be much easier than just typing this as I did. Of course, I didn't type. I asked Gemini to create this simulate data set, but it's basically, I'm going to run and then I can show you what this data set is. It's basically 3 feature collections that I just create that are these ones here. It's just a random sample over California where we have vegetation is one class that are the green points, water, it's the blue points, they are over water, of course. And then we have those here that are under constructed area, like over the cities. And I just want to create training an algorithm using satellite imagery to differentiate those 3 classes, as the same we did for crop classification. Of course, the algorithm, I mean, the feature engineering we're gonna do for crop classification, it's a little bit more advanced, but the idea is exactly the same. We're gonna use some ground truth data, some survey data for training an algorithm and then predicting the rest of the region where we don't have points, for example. So we're gonna use basically those 3 classes. So the first step is create the training data. So how we do that? I basically need to define what are the inputs I'm gonna use. On this case, I'm gonna use directly the bands of the satellite, band 2, that is blue, green, red, near infrared. I don't remember the 6 and the 7, but I just reflect short wave infrared, perhaps. I don't remember exactly, but I just reflectance bands from Landsat. Those are my inputs. The points are basically merging, like urban, vegetation, and water are those points that I just show here. I'm just merging everything to get 1 collection instead of 3. And what we'll do finally is using this function sample region that is basically transferring the band values from image to the points. It's basically over this point, it's gonna go to the image and store on a feature collection the reflectance value from B2 for B3, B4, B5. It's gonna prepare something like a table where we have observations and predictors. And class property is basically is the Y is the class 1, 2, 3, 1 for vegetation, 2 for urban, 3 for water, for example. And new FC is the merged collection, and finally bands are the bands I just defined here. So if I run that, I'm gonna uncomment this and then you guys can see the result. Look, we have 7 and 8 elements. There are points, and if I go to one of specific one here, for this point we have the reflectance for B2, for B3, for B4, and the land cover. So this is our training data basically. I just prepared the training data. Actually, this is the whole data set. Now I'm gonna split between training and testing. I'm gonna use the training for training and the other one I mean, in a perfect word, I should use the training, validation, and testing. Validation for fine-tuning the hyperparameters. I'm gonna skip this one and just split on training and testing. Look, here's I have the result. I'm gonna use this algorithm that is just a kind of clustering information. Yep, I think we have a question.
Right, one quick thing. So scale, why you keep scale 30? So sometimes scale varies, right? So that's why
Yeah, yeah. So why is 30? Is because, I mean, depends on the function I'm using. Sometimes it's important to remember the algorithm, the scale of the image, because it's gonna lose a reference. One is when I know that I need to restate the scale. It's basically if you go to the script here and put the algorithm and there is a parameter that is a scale, it's because you need to reset the scale. So that's what how I know when I need to state, to put in the code. Now, how I know the value, how I know that it's 30, why not 40, why not 50? So that's is because I know Landsat collection, the image from Landsat have 30-meter resolution. How I can access that information? We can search on the information related to the collection on the catalog, or you can use the projection nominal scales that is on the previous notebook, and then it's going to print on console the resolution of the image. That is going to be 30 in this case. And that's how I know that I need to use and the value that I need to put.
Yep, excellent. Yep.
So basically here I have the whole data set, and then now I'm gonna perform the training. So this is an example where I training using the whole data set. I'm gonna skip this one and I move to this. So what I did here, I'm gonna do exactly the same here. The only difference is gonna training using a fraction of the data set, not the whole data set, because I want to save a section for calculating creating the confusion matrix and calculate the accuracy, for example. And then how I split the data between training and validation. So the most easy way to do that is just create a column that it has random values from ranging from 0 to 1, for example, and then I'm just define a threshold for example 70%, and then all values that are low than 0.7 will be considering as testing. Everything that is everything that is lower than 0.7 will be training, and the rest will be validation, all testing in this case, for example, because this column is random, so it's gonna have randomly values between 0 and 1, and then if I get the ones that are lower than 0.7 will be wrongly 70% of the data. So, and then I store training and validation. They are still feature collections as the previous one, and that is the input of my model. And then on this case, for example, I'm gonna use random forest. I could use another one, as I'm just using random forest, for example. So training classifier using 70% of data. I'm gonna use this function, EE classifier, smile random forest. And then you guys can ask me, why I cannot use a random forest function for any library from Python? You can use, if it's not prepared for parallel processing, will be not processed on the server, will be slow. So if you guys want to use the power of the platform, it's recommendable to use the functions that are prepared for running on this infrastructure, and that's why we're using this EE classifier smile random forest. The 5 here, I don't remember, I think is the number of trees, but you can go back here on the documentation and check what is this parameter. There's another parameters that you can define as well. I'm just putting the default values here. And then we're gonna get, here we're gonna put the values you want for the hyperparameters, and then we're gonna use the function train. This is very similar for those are used to tidy models on R. It's the same idea. You prepare the model and then you train. So basically, EE classifiers, random forest, train, and then the features is the training partition. That is this one here. The class is the class property. What is this? If you go back here, we're gonna see that the class property is the land cover, is the name of the response variable, for example. And the input properties are the predictors that are all the bands. Bands also is a list with the name of all bands. Well, this is creating a training classifier that is going to store on trained classifier object. And then how we can apply this over an image or over we can apply over the testing data if you want to calculate the accuracy, and over an image if you want to scale up and do the predictions for all the region. I'm gonna apply first over the testing data, over a training, the feature collection in order to get the confusion matrix. So if you run that, we're gonna get the confusion matrix. So this is the confusion matrix. The class 0 is vegetation. We have, this is a really small testing data. It's just an example. For this, we have 7 points, and all the 7 were classified correctly. For 1, suppose it's water. For water, we had 8 points, and all the 8 were classified correctly. Because I know that it's correct because it is on the diagonal of the matrix. Let's suppose we had 1 here. It means that one of the points that were true were actually 2 were classified as a 0, for example. That what means if I had one here. So this is the confusion matrix. I mean, there's another matrix that I can calculate precision, recall, all this information I can retrieve from a confusion matrix. So this is how we validate or we test if the model is okay. If I want to predict, is the same. The only difference, I'm gonna apply over an image the classification instead of applying over a feature collection. And then the result is will be something like this. Look, it's really scaling up because I train with 7 data and I scale to world. Probably is super wrong, but I mean, you can get the idea. If you zoom here, you guys will see that always water was correctly classified as water. The green is the vegetation, and this is the areas where we have construction, a city or something, a road, something like that. So this is a way. I mean, you guys will see that it's really fast for training and for predicting. It's because it's doing in a parallel way. So just a small example how you guys can apply a really simple algorithm using Nerf engine. So this is actually my last script that I want to show you guys. Sorry if I go too fast and if it was too long, but the idea was just to show really a small sample of each section that we can, the things we can do with an Earth engine.
Any questions?
Again, I take the first, but I really enjoy it, and I feel like it can be implemented in so many different domain. And so I'm specifically interested, say, you can isolate Kansas, and then can you locate a specific area, say Ashland Bottom or Colby, and some of our lands, and extract some indices from some of the area we grow and make a little bit narrow and collecting the data during the growing season? Will that be a possibility? Can you just give some tips? How could we do that?
Yeah, I mean, it depends on. Of course, you can do using Earth Engine. There's any limitation for doing this. Perhaps the main limitation we're gonna have is the resolution of the image you can use, because depends on the nature of the. Let's suppose I want to predict yield on a field level, and we have a field with 100 acres. Of course, you can do, because I mean, we have different options of images you can use. You can use Sentinel-2 with 10-meter, Landsat with 30-meter modes. There's 250 or 500 meters. All are available options that you can use. Now, I want to predict a specific trait on a small plot unit that have 1 meter. Probably we cannot do using Landsat because it's 30 meter. Perhaps we can use some option from Planet No, I don't know. It's available on Earth Engine as long as you pay to Planet, and then you can use the products. It's not free for use, but you can use within Earth Engine as well. It's available. It's just not for free for non-commercial use, for example. So depends more on the resolution and the size of the target that you have and the resolution of the image than the process or the algorithm. I don't know if I answered the question.
Yeah, you explained it well. Like resolution is one of the bottleneck, right? 30 meter
Yep.
or 10 meter will not serve the small plots. But say if you get some high resolution, you pay for it and you get 3 meter or sub-meter resolution, and then can you incorporate shape polygons and extract information from a small? Okay.
Yeah. I mean, there's no limit that we can go. I mean, as long as you have an image with good resolution, is compatible with what you want to do, we can move forward.
And one
easily.
last question. So from your Git, like we can download and then use it on our own.
Yeah, it's available. It's publicly available. The only thing you need to do is making sure changing the project, because after you authenticate, it's gonna. I mean, you're gonna need to, you need to replace for a project that you're gonna create on your own account, and then you can use.
Yeah. So thank you, Dr. Raí. Thank you for your time.
No, that's a pleasure.
Any other question? All right, if there is no question, Raí, thank you so much for your time. I know it takes a lot of time to organize and prepare all the scripts, and I know you put a lot of effort on it. So thank you very much. It was very, very helpful, and I'm pretty sure everyone enjoyed it.
Oh, thank you guys. Thank you for the time that you also dedicate to that. It for me is a really big pleasure talking to you.
Yeah. Thanks to organizers also. And Dr. Raí, where are you positioned now? Like you said, you are working with GDM, but where you are positioned? Like what is your workstation?
Yeah, I'm working remotely. So actually all my team is working remotely. I mean, we are spread on US, Argentina, and Brazil. And I'm currently responsible for the data analysis on product placement. So basically the main responsibilities we have is on selecting the new genotypes, for example, for corn, wheat, and soybeans, and for making sure that we are doing the right recommendations. For example, density, sowing date, yield environment. So if you're indicating the right genotypes on the right yield environments, and then we end up using a lot of this because we use models for combining weather, satellite information, ground truth information for predicting, for example, the probability of response of a specific genotype for a specific environment, depending on precipitation, temperature, for example. And that's when we use this kind of information.
Yeah, thank you again.
No, thank you.
All right. Thank you very much, everyone. Thank you, Raí. And the record is going to be available on the AGSA channel on YouTube. Okay.